Hello everyone, welcome to Physics Mage. Dear students, today we have a problem based on wave optics. It will test your understanding about wave fronts and also like how the refractive index plays a role changing the pattern of wave fronts. Okay, so we will try and solve this problem. A transparent rectangular slab of length 20 cm and thickness 4 cm is placed in front of a converging lens of focal length 20 cm. A screen S is placed in the focal plane of the lens. Refractive index of the material of the slab increases linearly from mu naught at the bottommost face by an amount of delta mu, which is 2 into 10 power minus 4 between the bottom and the top faces. A parallel beam is made to incident on the slab as shown in the figure. What kind of light pattern appears on the screen? This is our question. So dear students, here they are saying that the bottommost plane, right, that will have some refractive index. As we move from bottommost point to the topmost point, the refractive index keeps on increasing linearly. So back to little basics. You know that suppose if we have a material in vacuum, the speed of light is c. If we consider in the medium, the speed of light will be slightly smaller, and the ratio of the speed of light in vacuum to the speed of light in medium, that ratio we know it is refractive index. Okay. Now, since in our given story here, say we have a slab like this. Let me just draw a slab. This is our given interest. We have light energy entering here. Imagine light energy falling here in the form of parallel beam. So we know that this is parallel wavefront. Energy is reaching at the leftmost end and it has to travel a distance of L here, right? So let's say this is L given. Okay. So light energy as it enters through this bottommost plane, so it has to be traveling, and when it reaches this bottom, the right side most point, right? It'll take some time for it. So delta t is the time taken, which is equal to L by speed of light in that layer. So we know that since the refractive index changing at every layer, right? Let me assume that the bottommost layer has a speed v. If bottommost layer has a speed v, then topmost layer, when the light enters at the topmost layer, right, like this, when it is entering at the topmost layer, it will be traveling for sure. And the speed of light in the topmost layer, if we consider that as v dash, okay, then it will cover some distance in the same time. So delta t equals, since the speed is different, right? So distance is also different. So let me take it as L dash. Since the topmost point has higher refractive index, so mu dash here is greater than mu here. So mu dash is greater than mu. So speed of light at the topmost point, right? The topmost layer, that is less than speed of light at the bottommost layer. So for sure we know that the length here covered, right? That is going to be small. From here to here, the length is L dash, let's say, from here to here. Okay. Now, what is the takeaway? When the light reaches here, let me highlight that point. When light, bottommost layer, the light energy reaches here, and the corresponding point at the topmost point will reach here. Remember, these 2 points belongs to the same wavefront. By the time the point A and B, right? Point A reaches point C, point B would have reached the point D. Okay, so C and D are existing at the same state of oscillations. Okay, so you can think of all other points which are corresponding to different layers, because at every single layer we have a speed of light being different, so they'll be covering different distances. So you can say that red color dots is a new wave front. Okay, but by the time D reaches, let's say, D dash, then C would have spread that influence in this medium vacuum, and let's say that information is carried. By the time D reaches D dash, C would have gone to some other location. So imagine that there will be a small sphere, that spherical wave fronts are created because of this point, and you can imagine from this point you can take one, say, I'm just drawing a tangent. Okay, so that if you keep drawing these spheres, at one point you can imagine that sphere pointing. Okay, so this one and this one, right? So you can have a new constructed wavefront like this. So that's your new wavefront. So this is your initial wavefront. This one is going to be a new wavefront. Okay, so you have this as 90 degrees. That is your C dash. Got it? So your C dash D dash would be your new wavefront. Now the light energy will flow like this. Light energy should flow like this. So in simple terms, what we have is a parallel beam of light is getting tilted like this because of varying refractive index. So this is the physics part of this. Okay. Now we have to understand few important ideas here. Whatever the distance we have here, right? It is L minus L dash distance. Okay. So remember, this is geometrical distance, geometrical length. Okay. And we know that when it is coming out here, it is already in the, when it is traveling, the energy is traveling from C to C dash, already energy is in vacuum. Okay. But D to D dash, when it is traveling, right, it is in the medium whose refractive index is mu dash, correct? So since the geometric length is this, and whatever the length we are going to consider now, that is like optical length. So optical length between D to D dash is nothing but mu times of L minus L dash. This is our optical length. Okay. So basically we are looking at the idea that, so D to D dash is the actual geometric length, but since we are dealing with optical length, it is slightly more than D to D dash. But remember guys, all this lengths, whatever we are dealing, right, that is going to be very, very small. But now look at this triangle. So C D D dash, this angle is theta. Okay, so we are dealing with tan theta. So tan theta, usually we would have thought like L minus L dash by D. That's a distance between these two layers, right? Okay. Now, instead of writing L minus L dash, you need to write mu dash times of L minus L dash by D. Why we are doing this? Because we know that this D to D dash, it's effective length. This is effective length, okay? Effective length between D to D dash by distance D is what we are considering. That will decide this theta. Okay, and why this theta is important? Because that will give us like what tilt that these rays are making with respect to the horizontal. Okay, once, because this is angle between the lines will be equal to angle between the perpendiculars. So that's the logic we are calling for theta. Okay, now anyways, so we will start solving this. So tan theta being equal to mu dash times L minus L dash by D. Now we already have the value of L, which is V times of delta T, and L dash is V dash times of delta T. And we need L minus L dash, which is V minus V dash times of delta T. Let us recollect that C by V equals mu. So V equals C by mu. So here we can write it as C by mu minus C by mu dash, that into delta T. So we have C delta T times mu dash minus mu by mu dash. That is our L minus L dash. So we can absorb this mu here and write C by mu delta T, right? That into mu dash minus mu by mu dash is what we have as L minus L dash. So let me call this as equation 1. So we know that this turns out to be L, and this is delta mu, and this is mu dash. So L minus L dash is this. So mu dash times of L minus L dash equals L times of delta mu. So substituting equation 2 in equation 1, we'll get tan theta being equal to, we have L delta mu is mu dash L minus L dash, right? That divided by D. So for small angles, because after all this change in the refractive index is very, very small. So you can write this is approximately equal to theta, which is L delta mu by D. And since in our story, the parallel beam of light falls like this, as this parallel beam is incident here, this gets tilted here as you're aware of it now. So the ray of light which passes through the optic center, right? That just goes without any deviation like that. And all the parallel beam of light, right? So this will get converged to that point. Gets converged to that point. Now you know that this particular angle that it makes with the horizontal, that is theta, right? So since this is theta, the height wherever this point, the image is formed, right? That is f times of theta. So our required solution turns out to be height will be approximately equal to the focal length times the delta theta, right? So delta theta, or just theta, right? That is L delta mu by d. This is what we have. Now suppose if we substitute the values of all these things, like focal length is 20 centimeter it seems, and length is also 20 centimeter. Delta mu is 2 into 10 power minus 4 number divided by d as 4 centimeter. So we get this as 5. So this is 100 centimeters. So basically it is 2 into 10 power minus 4 meters you will get. Okay. So that's our required solution. So dear students, I hope you understood this. And if you have any doubts, feel free to put that in the comment section. Thank you, everyone.